Have you ever stared at a word problem that just feels like a knotted up mess? With all these different pieces of information and you have no idea where to even start? Well, today, we're going to untangle that mess. We're going to look at the super elegant mathematical tool that's designed to turn all that chaos into a single perfect solution. So let's start with a classic scenario. Let's call it a tale of two pies. It comes from a school fundraiser, and it seems pretty simple on the surface. But hiding inside the numbers is a little puzzle, and it's going to take a very specific key to unlock it. Okay, here's our puzzle. You've got Gabriella's sale, you've got Scotland's sale. Same two kinds of pies, but different quantities and different totals. The question is, what's the price of one cherry pie and one pumpkin pie? It kind of feels like we're missing a piece of the puzzle, doesn't it? But are we really?
Turns out the answer is right there, hiding in plain sight. The real key is knowing how to look at these two pieces of information together. And the tool that lets us do exactly that, it's called a system of equations.
A system of equations is, well, it's pretty much exactly what it sounds like. It's a team of equations that are all related to each other. You can think of each one as a single clue, and when you put all the clues together, you can solve the whole mystery. In our case, the mystery is simple. How much for a pie? So before we jump into solving this thing with algebra, let's get a picture in our heads. Seriously, understanding what the solution looks like can tell us a ton about what kind of answer we should even expect to find. Here's the cool part. You can take any linear equation, like the ones from our pie problem, and draw it as a straight line on a graph. So if we have two equations, we have two lines. And since the solution has to work for both equations, there's only one place it can be, the single point where those two lines cross. The solution is literally the intersection. So if you think about it, what can happen when you draw two lines? There are really only three possibilities. One, they cross at exactly one spot. That gives us our one unique solution. Two, they're parallel. They run alongside each other forever and never, ever cross. That means there's no solution. Or three, they're actually the exact same line, just maybe written a little differently. In that case, every single point on the line is a solution, which means there are infinitely many of them. And, mathematicians have official names for these things. If a system has at least one solution, whether it's that single point or the infinite line, we call it a consistent system. But if there's no solution at all, like those parallel lines that will never meet, we call that system inconsistent. Okay, drawing lines on a graph is great for understanding the idea, but for getting a really precise answer, we need algebra. So let's dive into our first method, and it's a super powerful one called substitution. The logic here is actually pretty genius. First, you take one of the equations and just solve it for one variable. Get it all by itself, like y equals whatever. Then, and this is the brilliant part, you take that whatever and you plug it into the other equation in place of y. Suddenly, you have a new equation with only one variable. From there, it's easy. You just solve for that one and then plug that answer back in to find the second one.
Check this out. This system is like it was made for substitution. Why? Because look at that second equation. It's already solved for y. Step 1 is already done for us. We know for a fact that y is the exact same thing as negative 2x plus 1. One of our sources puts it just perfectly. This is the key move. We're going to take that expression, minus 2x plus 1, and swap it in for the y in that first equation. And just like that, poof, the y variable is gone, and now we've just got x's left to deal with. So after we do that substitution and work through the algebra, we find out that x equals 2. But wait, we're not done. We have to find y. We take that 2 and plug it back into the easier equation, y equals negative 2x plus 1. So y is negative 2 times 2, plus 1, which gets us to negative 3. So the solution, the exact point where these two lines would cross, is 2, negative 3.
But what if trying to get a variable by itself looks really messy? Well, don't worry, there's another equally awesome method called elimination. And yeah, just like the name says, it's all about making a variable completely disappear. So for this one, the first step is just to get organized. You stack the equations, lining up your x's, your y's, and your numbers. The goal here is to get the number in front of one of the variables, that's the coefficient, to be the exact opposite in each equation. Like a plus 2y on top and a minus 2y on the bottom. Why? Because when you add those two equations together, that variable cancels out. It gets eliminated.
Now, take a look at this one. It's perfectly set up for elimination. See how we have a plus y in the first equation and a minus y in the second? That's exactly what we want.
We don't even have to multiply by anything, we can just add them together right now. But hang on a second. What happens when you're solving a system and you end up with something totally bizarre, like -5 equals -12? I mean, that's obviously not true, right? So did you make a mistake? Nope. This is the math's way of screaming at you that there is no solution. These are parallel lines.
Okay, we've learned the theory, we've practiced the methods, now it's time for the payoff. Let's head back to Gabriella and Scott and finally figure out how much those pies actually cost.
All right, we have our tools, substitution and elimination. We have our puzzle. The very first step is to take that word problem and translate it into a language we can work with, the language of math. And here it is. Well, let C stand for the cost of a cherry pie and P for a pumpkin pie. Gabriella's sale gives us that first equation. Scott's sale gives us the second. Now, look at that. The 4 C terms are already lined up perfectly. This is just begging for the elimination method. Since both equations have that 4C term, elimination is definitely the way to go. All we have to do is subtract the entire top equation from the bottom one. The 4C minus 4C cancels right out, and we're left with a much, much simpler equation. 12P equals 192. Now, finding the price of a pumpkin pie is just one step away. And there we have it. Boom! A pumpkin pie costs $16. We plug that back into one of the original equations, and we find out a cherry pie costs $12. The puzzle is solved. We found the one and only set of prices that makes both Gabriella's and Scott's sales make sense. So why does any of this matter outside of a bake sale? Well, this exact same logic, using multiple clues to find one specific answer, is what makes so much of our modern world tick. Your phone's GPS? It's constantly solving a system of equations, using signals from different satellites to figure out your exact spot on the globe. Economists use gigantic systems, sometimes with thousands of equations, to model entire economies. This math is, quite literally, all around us. So we've just seen how 2 equations can help us find 2 unknown things on a flat 2D plane, which leaves us with a final question to chew on. What new dimensions, what kinds of new problems could we start to solve if we added a 3rd equation and a 3rd variable into the mix?